Welcome friends to today's presentation. Today we will be discussing about Poisson distribution. In my previous lectures, we have already covered about different types of probability, random variable, expectation, variance. Then we had studied about binomial distribution. In continuation to that, we now introduce a new distribution which is called as Poisson distribution. I am your Professor Dibyajyoti Bhattacharjee from the Department of Statistics, Assam University, Silchar. So welcome back to uh, the presentation on Poisson distribution. So Poisson distribution is basically used for modeling rare events and sometimes arrival rates in the field of business. But more specifically, it is concerned towards events which rarely occur. So let us start this presentation. What shall we cover in this presentation? That is the first agenda. So we will first try to understand what are rare events and how rare events becomes necessary in case of random experiments. And then we will understand about the Poisson distribution. We will know what is the Poisson distribution, what are the parameters of the Poisson distribution, and then we will see some real life application of Poisson distribution. And then we will see that how using the Poisson probabilities or the Poisson distribution, we can compute probabilities of certain events, and these help us in decision making, risk management, and planning of our strategies in business. Now let us look at this, what is world of rare events and about the arrival rates. Now Poisson distribution is actually used for counting type of data. That means when your random variables represent some count, number of times a particular event has occurred. So for a given period of time. So that is comes under the study of Poisson distribution, but there are some other conditions also for that. Now, let us take up some examples from this that, as I have told earlier, that Poisson distribution are more concerned with rare events. So, actually, we will look at the occurrence of the events which are relatively less frequent in the setup. For example, we take some examples from different fields of business and decision making. So, let us look at the operations management related to customer service. The number of customers arriving at a counter per hour. The number of website visitors per minute. The number of machine breakdowns per week. Now, if you look at this, maybe the first one, number of customers arriving at a counter per hour, you may tell that large number of people will arrive to the counter. But if the counter is not that frequent or visitors are not that frequent, for example, suppose I have a shop which sell cars, and then I have actually three sales representative whom I have given small cubicles where they sit. So let us assume that these are the counters. Now, people who come to purchase a car will be not in any other, like any other queue, like queue that we see for buying flight tickets or rail tickets or queue to a doctor's chamber, not that type. Because purchasing a car is almost say 3 or 4 times in a lifetime for an ordinary individual, maximum the 3 to 4 times in a lifetime people purchase car. So actually the number of visitors to the car, and then there are so many companies selling cars in a particular town. So the visitors to a counter will not that be frequent. So in an hour earlier, either you will get no visitor at all, or one visitor or two visitors. That means visitors coming to a particular counter in a particular time frame, say here in this case 1 hour, will not be very frequent. So such studies can be actually modeled, or such studies can be considered as an example of Poisson distribution, not a counter which actually doctors say appointment, distributing doctor's appointment, or a counter which is selling railway ticket. Those cannot be considered in this case. Okay. Number of website visitors per minute. Unless and until it is a very busy website, the number of visitors per minute is very small. So the time frame which actually makes the thing frequent or small. So maybe in a day there are many visitors, 30, 40 visitors. But if you look at a minute, there will be hardly, most of the minutes will not have any visitor, or may have some one or two visitors. And then maybe there is some incident suddenly takes place for which there may be so many hits in a particular website. So barring those time period, like say just after the stock market closes, you may find that there are a lot many visitors. Or some say website which is giving you the score of a match, cricket match, or a score of a football match. You may find that there are many visitors when the match is going on per minute. But when you, in general, when there is no match, you may find that or not a significant match is going on, you will find hardly any visitor in a particular. So those can be modeled using Poisson probability. Machine breakdown per week in an organization or in a company, machines are well maintained and maintained properly. So breakdown will be less frequent. In a week, there might be no breakdown or maybe one breakdown, another machine breakdown, which is even more rare, two machine breaking down in the same week. Now let us take some examples from finance and risk management. Number of loan defaults per month. So another rare event. Number of trades executed per second. So in case of trading, number of cybersecurity attacks per day. So these are rare but not unprobabilistic. There is a chance of things taking place. Number of errors. So we have some examples from quality control and logistic. Number of errors in a code repository per 1000 lines. So these are very sophisticated codes are written, and so in that finding an error in 1000 lines is not very frequent. Number of shipping delays per 100 deliveries by a good transporting agency. There will be hardly any delay on means whatever promise they generally keep up to that. So these are some examples where you have some rare events or some arrival rates which are relatively less frequent than others. So such things can be modeled using the Poisson distribution. Now let us look at Poisson distribution. What is a Poisson distribution? A Poisson distribution is a discrete probability distribution. Discrete means here the random variable which we are considering or the variable of the distribution takes a discrete values only. That means it takes integral values like 0, like 1, like 2, like this. It will keep on telling. That expresses the probability of a given number of events occurring in a fixed interval of time or space. That means with the help of this distribution, we can compute the probability that, for example, say one failure or two failures in a particular hour. If these events occur with a known constant mean and independent of the time since the last event. That means if the event has occurred once, uh, and then the next event when it will occur, they are not connected to each other. So events are considered to be independent, and the chance of failure is, or whatever be the probability of occurrence of that event, that rate remains fixed. Rate will not change. For example, if you think of a machine which has been working for long hours, the chance of failure may increase at the late hours when it has already functioned for 7, 8, 9, 10 hours. The chance of failure might increase, or the rate of failure might increase when it has already worked for some much such hours. So these type of things cannot be considered under Poisson distribution. This means the failure rate or the chance of the event to occur, the rate that the event will occur is not dependent on time. So this is one important assumption of the Poisson distribution. So first thing is that Poisson distribution assumes about the independence. That means the occurrence of one event does not affect the occurrence of the another event. So the events are not connected to each other. Next, the constant rate, the average rate that is events per interval is constant. The constant rate is that is having a constant rate lambda. The average rate events per interval that remains constant. Impossibility of simultaneous events. The probability of two events occurring at exact same instant is effectively 0. So this is an assumption which is lesser discussed. But first two assumptions are really something to be taken care of and might often get violated. In that case, our probabilities computed might not give us reasonably reliable results if the assumptions get violated. Now, let us look at lambda, that is, which is also called as the parameter of the distribution. It is the rate in which the event is occurring. So, the Poisson distribution is uniquely identified by a single parameter lambda. That means in case of binomial distribution, if you remember, we had two parameters. One is n, number of occurrences, and one is p, that means probability of success of the event, that we found in case of binomial distribution. But in case of Poisson distribution, we have only one parameter, that is lambda, and that is actually the number of the rate of occurrence of that particular event. So since it is a rate of occurrence, so this lambda has to be greater than 0. However, you cannot put a upper limit on lambda. It may go infinitely, but since it is a rare event, so rate of happening of the event in a given time span will be positive more than 0, but it will not be very high. But means there is no restriction. It can go up to infinity also. But generally for Poisson distribution, it does not go up to that height. Okay. Lambda is also the mean, and it is as well as the variance of the distribution. That means if a random variable follows Poisson distribution, then expectation of x and variance of x is equal to lambda. So this is a very interesting property. Notationally, we write like this. That means if we want to tell that x is a random variable which follows Poisson distribution, then we write it like this: x follows Poisson with parameter lambda. This is read as the random variable x follows Poisson distribution with mean lambda or parameter lambda or rate lambda. So these are different ways. Crucial insight: you must define the interval clearly. Interval here means time interval. The rate of occurrence of the event in an hour, rate of occurrence of that particular event in a minute, because that actually makes the event rare or frequent. The interval which makes it this. For example, lambda equal to 2 customer complaints per day. So suppose I am having a service center and I am also open to complaints. That means if someone is not satisfied with the performance, they have every right to make a complaint. In that case, if lambda equal to 2, it means that I have 2 complaints per day. Okay. Lambda equal to 0.1 network failures per hour. So this is how lambda is defined. That means we not only give the value, but also we give the time interval, because this is a rate after all. So you need to tell out what is in the denominator, per what, day, hour, second, minute, whatever. Lambda equal to 15 cars arriving at a drive-through per 10-minute period. Now you see here lambda is 15. That means lambda can go up to a large number of values also. And then 10-minute period, it means the 10-minute period is quite high. And in 10-minute period, you have on an average 15 number of things landing up, 15 number of cars coming. So if you want to keep lambda reasonably small, you may, instead of taking 10 minutes, you can write that lambda equal to 1.5 per minute. So that way you can control the value of lambda also by changing the time interval, but not necessary. This is just a matter of concern. Okay. Now probability of occurrence. So we now introduce the formula of the Poisson distribution, or the probability function of the Poisson distribution. Now remember, I told earlier that this is a discrete distribution. That means the random variable takes a discrete values only, and in such cases the corresponding probability function for any discrete random variable is called as the probability mass function. So here the probability mass function is given by this expression. That means probability that capital X, this is the name of the random variable, and this is the specific value taken by the random variable. That means this may take values like 0, 1, 2, small x, but x is like a symbol. It actually represents the random variable. So probability that x takes a particular value is given by e to the power minus lambda, lambda to the power x by x factorial, where we have probability x equal to x, probability of exactly x number of events taking place. This E that you see in the formula, it's the natural logarithm. Its value is 2.718282. I am speaking about this. This is a constant. It's the base of the natural logarithm. So it's 2.718282 e to the power minus lambda. Lambda is the rate. So lambda is the rate or the average of the event. So that's all. And x is the random variable which represents the number of events. So once you know this, suppose I want to find out that what is the chance that the target is been hit 3 times, given that x follows a random, x is a random variable following Poisson law, then I will write x follows Poisson law, Poisson, Poisson law, and I also have to tell the value of the parameter that is I may take. Okay, well, it's like say 1.2, that for in 1 hour. That means lambda equal to 1.2 per hour. So in that case, what happens? We have the now Poisson distribution e to the power minus lambda. That means in place of lambda, I will replace 1, 2. And you will tell me that compute the probability of x equal to 0, x equal to 1, whatever, In that case, in place of x, I will replace the value. Now there is a term, this time in the denominator. I think some of you might not be acquainted with this. This is called as x factorial. So x factorial, what happens? Suppose I take an example of 4 factorial. It is the product of numbers starting from 1 going up to that particular number, all natural numbers. Product of all the natural numbers starting from 1 to that particular number. Suppose I have write 5 factorial, then it will be 1 into 2 into 3 into 4 into 5, or you can write 5 into 4 into 3 into 2 into 1, meaning is same. So what I do is that I start with the highest value and then keep on decreasing it by 1. Ultimately, we reach 1 and then we stop. We don't multiply it by 0. So here is an example of 4 factorial. You can see that it is 4 into 3 into 2 into 1. So this value comes out to be 24. So 5 factorial, if you multiply, then you will get 24 into 5. So that is equal to, so you get this as 24 into 5. That is equal to, because 4 into 3 into 2 into 1 is 24. 24 into 5 is 120. One thing you may note from here that these values 1, 2, 3, 4, this is my 4 factorial. Okay. That means what happens, what I am reaching here, that means I am reaching that, okay, 5 factorial can be written as, 5 factorial can be written as 5 into 4 factorial. Okay. 4 factorial. So this is an interesting, that means if I have n factorial, I can write n factorial as n into n minus 1 factorial. So this way I can write the thing. So these are the different ways in which we can write the probability. How we can compute the probability of a Poisson variable. Now let us start directly with a problem. Here is a problem of staffing a customer service line. A bank's call center receives on an average lambda calls per hour. So here you see lambda, here per hour is there. So we are, sorry, not lambda, so 3 calls. So we get the value of lambda here, lambda equal to 3 per hour, or we can use lambda equal to 3. What is the probability of receiving exactly 5 calls in the next hour? So this data I have from my previous experience that in an hour there are generally 3 calls. So what is the chance of getting 5 calls in the next hour? So let us have this. Let us first identify the parameter. What is the parameter? Parameter is x lambda equal to 3. So this is, we have the value of the parameter, that lambda equal to 3. This is the value of the parameter. Now what are the other things we require compute? We want to get the value of x. That means number of calls. So that is x equal to 5. So now we replace this. So we replace in the formula probability of x equal to x. We write the formula e to the power minus lambda, lambda to the power x by x factorial. Now this is e to the power minus 3. Okay, e to the power minus 3. And then this one lambda is 3, x is 5. So this is 3 to the power 5. And this is 5 factorial. 5 factorial is 120. Let me write it here. And then 3 to the power 5. That means if you multiply 3 5 times with each, 3 into 3 into 3 like that 5 times, then you get 243. So that is value of 3 lambda to the power, sorry, lambda to the power 5. Yeah, 3 to the power 5. And then e to the power minus 3. So e, we found that it is 2 point, in the previous slide we have declared the value 2.718282. So this is, so we have this as 2.718282. So this is the value of e, and then to the power minus 3. Okay, to the power minus 3. This value, when we actually compute in examination or in some other situation, this value is generally given to us. If it is not provided to us, then if you use Excel, then fine, you can find the value, or else you can actually use a scientific calculator to find e to the power minus 3, e to the power 3, like that, whatever value. You can find it out. And then we see, so ultimately we get the probability, we replace this. So for 243 into 0.0498. So this is equal to 12.094 divided by 120. So ultimately you get this as 0.1008. So this is equal to 1008. So what is the interpretation of this computation? So problem is over. You have compute, you are asked to compute the probability, so you have technically computed the probability also. So let us see what is the interpretation. This is approximately 10.1. How did I get 10.1? You actually multiply whatever probability you get by 100. Not necessary, means problem is over. But in interpretation, percentages actually is relatively easy. So you have the, you have the probability as 0.1008 multiplied by 100. So this will give you 10.08. Approximately, it's 10.1. 10.1. So there is 10.1% chance that in the next 5 hours, you will, in the next 1 hour, you will get 5 calls. That means 5 calls you will get in the next hour. That probability is 10.1%. Next comes about system failure, operation risks. A server cluster experiences an average of zero point 0.2 critical failures per day. So a server is there which experiences a failure, average rate, that is lambda value is given to you 0 0.2 per day. What is the probability of having no failures in a day? That means if x is the random variable representing the number of failures, so no failures means x is taking the value 0. So let us first write down that what all things we have. So firstly, we have that the rate, that is lambda, this is equal to 0 0.2. That means number of failures per day is 0 0.2. And the event that we want to compute, that is the random variable, that x is no failure means x equal to 0. Now we come to the formula, e to the power minus lambda, lambda to the power x by x factorial, that is the formula. So this is my formula. Here we place in place of lambda 0 0.2. Then lambda to the power x, we have 0 0.2 to the power 0 factorial, to the power 0 and by 0 factorial. Now 0 factorial is 1. You might think that 0 factorial might be 0, but there is a formula which proves that 0 factorial is 1. And anything to the power 0 is 1. So this is also 1. So ultimately, we are left with e to the power minus 0 0.2. That value is 0.8187. That means ultimately, your probability value comes out to be 8187. Now multiply it by 100. So if you multiply it by 100, you will get 81.87, approximately 81.9%. Now 81.9% chance is there that the system will not fail. So that means you will enjoy a failure-free day. That means the chance is almost 82%. It's quite high. That in another words, you can tell it like this: that if I go to my office 100 days, out of these 100 days, I will not be able to see a failure in 82 days. So that is quite high probability. That means your server is working well. But however, you may tell that it can be increased further. So, well, then you need to decrease your lambda, number of failures per day rate. That rate will decrease, then the probability will increase further. Okay. Calculating at least and at most probabilities. Sometimes we are interested, or managers are interested to know things in at least, that at least there will be one failure. That means either zero failure or one failure. That must will resist, but not more. So, okay. So managers often need probabilities for ranges of outcomes. So here we are using the same example of a call center. But here we, instead of computing the probability at a particular instant or particular fixed value, we are using at most and at least. So let us look at the question that we have lambda equal to 3 that we have already computed. At most 2 calls means maximum 2 calls. That in the next 1 hour, a maximum of 2 calls will be coming. Maximum. That means 0 will also be okay. I am okay with 0. I am okay with 1. I am okay with 2, not beyond that. That means the number of calls at most value will be 0, 1 or 2. So what is the formula for that? Formula is same, just we have to calculate the probability of x equal to 0. So this is how we calculate x equal to 0. I am not going to discuss it because we have discussed it, how to calculate the value from Poisson distribution in the previous 2 illustrations. Then I also need to compute, like after computing x equal to 0, I also need to compute x equal to 1, because we are calculating at most 2 calls, that means 0, 1 and 2 calls. And then we need to compute x equal to 2 also. So we compute, we find that it is 0.224. Now at most means I am satisfied with 0. I am satisfied with 1, I am satisfied with 2, but not beyond that. So this is the sum of the probabilities. So I have written it once again. X equal to 0 is this 0.0498, x equal to 1 is 0.1494, x equal to 2 is 0.224. Now calculating at most is the sum of this. So x equal to 0 plus x equal to 1 plus x equal to 2. So we get this as 0.4232. So that is x less than equal to 2. So there is a 42.3% chance of a very quiet hour. Quiet hour means there will be not more than 2 calls. So 42% days or 42.3% chance that there will be no call or very few call, not no call, very few call, like either no call or 1 call or 2 call. Now calculating at least. Now what happens? At least is 2 or more. If I tell that at least 2 calls, as was asked in the question, what is the chance of getting at least 2 calls? Now at least means 2 or more. That means you have to calculate for 2, you have to calculate for 3, you have to calculate probability x equal to 4, you have to calculate probability x equal to 5, and as you can see that in an hour there can be infinite number of calls, so it will go up and it will be a huge computational disaster. Means throughout the day we'll keep on computing. A easier way is that you calculate the complementary event. That means you are interested in x greater than equal to 2. You calculate the probability of x less than 2. Subtract it from 1, that is the total probability, and then you get the residual. What remains is what you want. That means probability of 2 or more number of calls. So the complementary event is like this one, x less than 2. So when I write x less than 2, this will give me x equal to 0 and x equal to 1. When I replace this value 1 minus, this is x equal to 0, this is x equal to 1. When I add up, I get this. So 1 minus this is 0.8008. So probability of x greater than equal to 2. This is 0.8008. Then there is 80% chance of getting 2 or more calls, because point you multiply by 100, then you get 80.08. So there is 80% chance of getting 2 or more number of calls. Okay, so this is how we compute the probabilities of at least and at most. Obviously, calculation increases a more. Now let us see that what are the values of the probabilities when we actually keep on changing the value of the parameter lambda. Now binomial had 2 parameters. We had seen this exercise for binomial also, if you recall, where we kept n fixed at 10 and we have changed the value of p and see how the curve changed. But here not like that, because we have only one parameter and that is lambda. So we compute the probability of x equal to 0, x equal to 1, x equal to 2, dot dot up to, you can go to any value. But anyways, very high value will not yield any probability, very close to 0. Now if you look at this, when my lambda value is less, the probability takes this shape. Now these are probability mass function, like binomial distribution. Poisson distribution is also a discrete distribution. So you will not get probability in between. That means if you tell me that what is the value, that 0.5 probability of x equal to 0.5, lambda can take fractional value, no issues. But x cannot take fractional value. So x will take the value 0, 1, 2 and dot dot up to infinity. So I have taken up to 10. I can extend also. And I compute the probabilities. First probability is very high. It's like very close to 0.7. Then it comes down to very close to 0.3. Then it comes out to it is very close to 0. And then these are very, very close to 0. And in some cases, they are so much close to 0 that we can hardly differentiate. Now, if you look at this, we cannot connect them because this x cannot take fractional values. But if we just for the namesake we draw a line, then we find that the line dips down very quickly and becomes almost parallel or equal to x-axis at the later part. Now increase the value of lambda from 0.4 to 1.2. Initially probability is 0.3, goes up to close to 0.4. Then it starts coming down. And after a stage, it becomes very close to 0. But look at the, connect them by a dotted line. Then you see there is a tendency of this. That means it is right skewed. It is having a curve which is having a long tail in the right side. So this is right skewed curve. Then we increase the value of lambda further. As you can see here, we have lambda equal to 2.2. And then what do we see? That initially it has shown an increase. but at a slower pace, and then it starts decreasing rapidly, and then after some time it becomes very close to zero. And then if you look at this further value of lambda, I have increased to 3.6, then you can see this as lambda like this. Now you see further, if you increase the value of lambda, these will have a tendency to form a normal curve. And then further, if you keep on increasing, then you will see that the probabilities are distributing in such a way that you get a longer tail in the left side and a shorter tail in the right side. So this is the entire story about Poisson distribution. And this is how the curves form. That means if you go for higher values of lambda, you will find that the curve is becoming uh, negatively skewed. But if you look at smaller values of lambda, you will find that there is a distinctly positively skewed curve. And for reasonably finite values of lambda, you will find that it is taking a normal shape. So this is about the shape properties of the Poisson distribution. Now let us look at some of the properties of Poisson distribution. First is that the mean of the distribution is the value of the parameter itself. We have earlier discussed it also. And mean of the distribution and the value of the parameter are same. Same can be told about the variance also. That means the variance of the distribution is also having a value lambda. The standard deviation of the distribution, as we know, is square root of variance. So that is square root of lambda. And ultimately, what we'll end up that this is a distribution in which mean is equal to variance. So from the raw data, if we compute the mean and we find that the mean and variance, we may not find it's very close, same value, but very close. If the value of the mean and the variance are coming very close, in that case, we can assume that, well, this data set, provided the data set represents a discrete value 0, 1, 2 like that, then we can understand that it probably comes from or follows a Poisson law. And in such a case, the data will nicely fit a Poisson distribution. So this is an important feature, but not necessarily equal, but even equivalent, close, mean and variance. Okay. Now let us bring a comparison between binomial and Poisson, because both of them are discrete distribution. Now what is the common thing? The common thing is that both of them are discrete distribution. uh, X takes value 0, 1, 2. Binomial also X takes value 0, 1, 2 like that. But then what are the other things? Number of trials. In case of binomial distribution, you find that the number of trials is fixed. You can see the first point here that the number of trials are fixed. Now n is also the parameter of the distribution. Here it is theoretically it is not fixed. That means number of times you repeat an experiment, and that is actually not influencing much like your value of, because your value does not depend on n. But theoretically, it is not fixed. You can take infinite values also. Focus. The main focus means the purpose. In case of binomial distribution, we are to find out that number of successes in n Bernoulli trial, or in n trials are there, a number of trials are there, where each of the trial follows is a binomial variable. That means either failure or success. In that case, what is the chance of getting X successes in n repetitions of Bernoulli trial or binomial trials. But here actually we are interested in finding out the number of events in a particular time frame. Now, how to compute the probability? Here the probability is computed by the mean rate of arrival, this lambda. With the help of this, we compute the probability. And here there is an assumption that the probability of success remains same throughout the number of trials. That means if I repeat the trials n number of times, each time the probability of success should remain the same. Under that condition, the probability can be computed. Here also it is same, but here it is not the probability, it is rate of occurrence of that particular event. So since it is rate, it can go beyond 1 also, but it should be positive definitely. You cannot have a negative rate for this type of experiments. Now this is when it is best. When it is best, that is Poisson distribution is best when you study the rare events. Rare events is corresponding to the time frame. Whatever is rare in a small time may be very frequent when you consider a longer time frame. So that is a very important characteristic. And then here it is best when you try to find out the probability of proportion X successes in n trials. So those cases binomial distribution is more frequent. There is a rule of thumb also. In a binomial distribution, if n is very large and p is very small, that means probability of success is very less, but you have freedom to repeat the experiment a large number of times. In such a case, n into p is a reasonable finite number, because n is very large, that means n is tending to infinity. P is very small, so small that when you multiply it with infinity, then it gives you a reasonable finite number. Then a binomial distribution becomes Poisson distribution. That means in a binomial setup, when you repeat the number of experiments large number of times, in the if you remember, there was an experiment where we found that the value of n is I think 40, or in the binomial example, we had one such example where we had to find out the value of n, and then when we computed, we found the value of n. I think we found 200 or something like that. Very large number it was. So 200, n equal to 200. So these are actually examples where your repetition of the experiment goes up very high. And if the probability success is very small, then what happens? Out of 200 repetitions, you will hardly find that there is a failure. Means there is a failure. For example, suppose there is a bus stand near my home, which from where buses leave for the airport. So people who live in and around my home or in the city and want to go to the airport, they come to this bus stand, because everyone knows that at 5 a.m. in the morning there is a bus which starts from this particular stand and goes to the airport. Because getting some vehicle in the morning is very difficult, but that bus is always there. Now, I had also availed this service a large number of times, but one day when I went, I found that the bus is not going. I asked the uh, station master. The station master told that there was a breakdown early morning when I started to wanted to bring the bus to the stand. So today bus will not be going. That means out of many days I tried to go, say maybe 50, 60 days. One day the bus did not go. Other days whenever I went, the bus was ready. So that is a rare event. That means you are allowed to repeat the experiment large number of times, and the probability of success here means breakdown of the bus is very rare. In such cases, we will find that the binomial distribution tends to Poisson distribution. That means whatever probabilities we compute with binomial, that can also be computed with Poisson, provided these two conditions are satisfied. Three conditions actually: n should be large, p should be small, and np should be a reasonable finite number. So these three conditions satisfied, then we can approximate the binomial probability with a Poisson probability. Now let us look at that if we want to use Excel for computing. So is there any way we can calculate the Poisson probability with the help of Excel? Because you see, we need the value of e to the power lambda minus lambda. So that may not be easy to compute, because nobody can summarize, because lambda value keeps on changing. You can remember the value of E, that is 2.718282, but then e to the power minus lambda, that obviously, because lambda value keeps on changing from experiment to experiment, not possible. So you need to take the help of a scientific calculator, compute it, multiply with some number, divide it by some number. Difficult computing. So is there any Excel formula? Definitely yes, there is an Excel formula. In any cell you write Poisson distribution, then give the value of the random variable, that is 3, 2, 1, 0, whatever, and then comma lambda, that means the rate, and then comma false. That will give you the probability at a point. We have an example also: x equal to and lambda is 0, 4. Then in Poisson, what will write? Sorry, Excel, what will write? In any cell will write equal to Poisson dot dist. Then x is 2 and lambda is 0.4, comma false, because false will give me the probability. But if we write true, then we will get cumulative probability. That means cumulative probability is probability of x less than equal to 2. That means if you look at these two expressions, these two Excel formula, this one and this one, you will find that they are same, only difference is in false and true. So what actually difference they make? The difference they make, this gives you probability of x equal to 2, and this will give you probability of x less than equal to 2. So this is called as the cumulative probability. This means probability up to that value of x. So that is cumulative probability, and the other one keeps probability at a point. So depending on purpose, sometimes it might be more important cumulative probability than probability at a point. Okay, now let us look at some real life examples. Suppose you want to find out that how many hotel rooms to overbook, how many support staff to schedule. Now you see, I had been to a particular place, and then one day I decided that let me have some time, so let me see whatever. As I went to a big city for some medical treatment, then I went to a nearby place because the hospital was closed on Sunday. So I went in a Saturday. I went to a nearby place, and then I found that there and booked a hotel. I was staying in the hotel. When I went Sunday morning, I found that a lot of people are there. They are taking breakfast and all. Now in the evening, I could not find any person. So when I asked the hotel people, they were telling that no, actually most of the people have left because they generally get customers in the weekend. Weekend they are means never goes rooms does not go empty. But there are a lot of demands for rooms in the weekends, but very few demand for rooms in weekdays. So number of demands for room in weekdays, that can be computed using a Poisson distribution. And if the probability is high, that means there will be some booking for the room coming in, even in weekdays. This will help them to schedule the support staff which is required. If there are, if the probability of demands coming is some high values, the probability of demand more than equal to 5 is more than 80%. That means there will be more than 5 demands. That chance is 80% or even more. In that case, they will keep reasonable number of staff because 5 and more number of rooms getting occupied. So you have to provide all the services, isn't it? So this is how Poisson distribution can be helpful in modeling because you can compute the probabilities if you know the rate beforehand. Risk management, quantify the risk of extreme events, that is multiple loan defaults or cyber attacks in a single day. And this actually helps in determining the capital reserves or security of investment. Number of people who claim their money back. So from a stock. This can be actually modeled using Poisson distribution. Quality assessment, manufacturing, monitor the rate of defects lambda over time. A significant increase signals a process that is out of control. A significant increase in significant increase in probability actually signals that the process is going out of control. That means in some quality maintenance exercise, it may be such that number of defects are very rare. Now, if the rate goes up or the probability of getting defect increases, that means there is a signal that the process is going out of your control because in a normal situation, you will not get so many uh, defect alarms. Okay. Now, before we conclude, let us make a summary of the things. The Poisson distribution is generally used to model rare independent events over a particular interval of time. The distribution is defined by a single parameter that is generally represented by sigma, and the probability mass function is given by probability of x equal to small x equal to e to the power minus lambda, lambda to the power x by x factorial, with lambda greater than 0. So lambda is positive, and the value of the random variable can be 0, 1, 2, whatever it is. The mean and variance of the distribution is lambda. This is called as the key property. Use Excel's Poisson dist function can be used to avoid manual computation, and you can get the result correct using Poisson dist function of Microsoft Excel. This is a powerful tool for capacity planning, risk management, and quality control. Some of such examples we have seen in this presentation. So with these words, we come to an end of Poisson distribution. So we have done some problems. Also, we have seen the mathematical form of the Poisson distribution. We have also seen how we can do the computations with the help of Microsoft Excel. Thanks a lot for your patient listening. If you have some query in mind about Poisson distribution, you can write it in the comment box below. Or if you want to make it private, then you can email me. This is my personal email ID. Thanks once again for watching the video.